We're going to look at parametric equations. And with parametric equations, instead of y being dependent upon what x is, we have two separate functions, one for x and one for y. So x and y are dependent on a third variable, and we usually label that variable t. For the exercises that we're going to do in the homework, the instructions say, in exercises 3 through 20, sketch the curve represented by the parametric equation. We're going to graph this parametric equation. Indicate the orientation of the curve, in other words, as we graph, which direction is the graph going, and write the corresponding rectangular equation by eliminate the parameter. And we'll talk about that a little later. In this case, we're going to take negative, well, most of the time, we're going to use -2 to 2, the integers from -2 to 2, but we won't always do that, and I'll show you some examples where we don't. For this one, -2 to 2 will be just fine. If we plug -2 in for t to the third for the x coordinate, we get -8. If we plug -2 in for the y coordinate, -2 squared is 4, 4 divided by 2 is 2. And then we plug in the rest of the values. So plugging -1 in for t to the third will give us -1, and in for the y will give us 1/2. 0 gives us 0, 0. 1 gives us 1, 1/2, and 2 gives us 8, 2. Now if we plot these points, we get -8, 2, 2, 3, 4, 5, 6, 7, 8, 2. Then we get -1, 1/2, 0, 0, 1, 1/2, and then finally 8, 2. And then we draw the curve. And the direction it went was left to right, so we just draw some arrows indicating how this curve was created. Well, now we want to draw, or we want to create the rectangular equation, meaning our typical y equals, or even in some cases, if it's more convenient, we'll have x equals. In this case, I guess we could go either way with this one. If we have x equals t to the third, we want to get x by itself, or t by itself, excuse me, t by itself. So we'll take the third root of both sides, and we get the third root of x equals t. Now we have this other equation with y over 2, and we want to replace the t, we want to replace that t with the third root of x. We have y equals the third root of x squared over 2. And there's your Cartesian equation, or rectangular equation. And if you graph y equals the third root of x squared over 2, you will get the exact same equation. In the next example I have, same instructions. We have x equals the square root of t, and y equals t squared minus 2. In this case, I chose not to go from -2 to 2, but rather the perfect squares 0, 1, 4, and 9, because if you see, we have the square root of t in the x equation. Now the square root of 0 is 0, 1, 2, and 3. And for y, we have 0 squared minus 2 is -2. 1 minus 2 is -1. 16 minus 2 is 14. And 81 minus 2 is 79. So maybe we won't worry too much about very large numbers. Hopefully we'll get the idea without having to use those. The first point is 0, -2. Then we have 1, -1. 2 goes all the way out to 14. So 2 is, or not out to 14, excuse me, up to 14. 2 is already way up here. This is what it looks like right there. And if we indicate the direction, it's going in an upward fashion, so to speak. Now we want to write this in Cartesian equation, and I want you to notice that because we have the square root of t here, x will never be negative. So x will always be greater than or equal to 0, and that's important to note when we write the Cartesian equation. We have x equals the square root of t, square both sides, you get x squared equals t. noting the fact that x still has to be greater than or equal to 0. You can't take the square root of t and get a negative answer, therefore you cannot allow x to be negative. Now we're going to plug x squared in for t. We have t squared minus 2. And we have y equals x squared squared minus 2. So we have y equals x to the 4th minus 2, and noting that x has to be greater than or equal to 0. And there is the complete problem. In my last example that I want to show you, we have x equals 2 cosine t and y equals 4 sine t. The values I've chosen, rather than negative 2 to 2 or even perfect squares, I chose one that values that can be easily answered using cosine and sine. So if I plug 0 in for 2 cosine, I get 2 times 1, which is 2. The sine of 0 is 0, so we have the point 2, 0. Pi over 2 for cosine is 0, so we have 0. Plug pi over 2 in for sine. We have 4 times 1 is 4. The pi, cosine of pi is negative 1, so we have negative 2. Sine of pi is 0, so we have 0. Cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is negative 1, so we have negative 4. And then 0 and 2 pi are really the same thing, so that's going to be the same point. Well, if we plot these points, we have 2, 0, 0, 4, negative 2, 0, and 0, negative 4. And what this creates is an ellipse. It's one of the more famous parametric equations. Not the 2 and 4 necessarily, but the one that creates an ellipse. Now we have to get this to be Cartesian. And what we know is, and I have the hint, use Pythagorean properties. We have sine squared t plus cosine squared t equals 1. And in this case, if we get cosine t by itself, we'd have x over 2 equals the cosine of t. And as far as the y equation, we have y over 4 equals sine of t. Now if we replace sine with y over 4 and cosine with x over 2, you get the following. Y over 4 squared plus x over 2 squared equals 1. And finally we get y squared over 16 plus x squared over 4 equals 1. And if you remember your conic sections, that's exactly what the equation is for an ellipse.